Hello, and welcome to yet another lecture on functional programming. My name is Dmitry Soshnikov, and today we will talk about quite complex topic, namely category theory. When we started talking about functional programming, we began with mathematical concepts such as lambda calculus and equivalent mathematical theory combinatory logic. And lambda calculus is typeless theory, so we can extend it with types. And typed lambda calculus forms the basis of functional programming languages. We can define things like numbers, pairs, lists in pure lambda calculus. So you can say that we can build a foundation, the logical mathematical foundation, to what we have been using as a functional programming language. And on top of the functional programming language, there is also some pragmatics. How do we define data types? How can we define data types in such a way that they can be used effectively? So we started and we have talked about purely functional data structures and things like sequences, things like continuations, and so on. However, we can view functional programming from yet another angle, from the angle of another mathematical theory called category theory. And category theory is, in fact, very abstract mathematical concept. It is, in a way, similar to abstract algebra when we start thinking about compositional properties of objects without regard to their internal structure. So we basically talk about how things are related to each other, how those relations can be composed, and those kind of very abstract things. And interestingly enough, this category theory can be used in many areas of mathematics, such as topology. It is useful in some areas of theoretical physics, and interestingly, in computer science, in functional programming. And that is something we will talk about today. So let me start by introducing the concepts of category theory. And if you want to go into some more detail on this topic with examples in other programming languages such as C++, I highly recommend you the series of blog posts by Bartosz Milewski, which is called Category Theory for Programmers. It's quite a long series of blog posts, so it will be definitely broader, much broader than we will talk about today. But it is really useful reading. Some of the blog posts have been translated into Russian and published on Haba. So you can find the translations on the internet, but complete series of blog posts in the original English form can be found from this link. And again, this is the very good place to start learning this category theory. But let me give you some introduction. So category theory introduces the notion of category. And category is basically a set of objects, which is denoted by ob of k. K is category, ob of k is the set of objects of that category. And those objects are related by arrows, which are called morphisms. And the set of those morphisms is denoted by more of k. So it can be drawn or represented graphically using something very similar to a graph, objects and arrows between them. However, there are several differences between graphs and categories. In categories, we are not limited to one arrow between objects, so objects can be connected by numerous arrows, and those arrows would be different ones. So it's not like one edge of a graph. Also, category has some important properties. So for any arrow f from A to B and another arrow G from B to C, there is a compositional arrow. It always exists, which is called G composition F, which relates A to C. And that is quite natural property. So if this is A, this is B, this is C, so this is the composition of F and G, if this is F and this is G. So there always exists a composition. And also for any objects in the category, for any A in objects of the category C, K, there exists always an identity arrow from A to A. So every object in the category has this kind of identity arrow. You can think of it as an identity function, of course, but speaking categories, we are talking very broadly. So it's just an arrow, and we are not discussing like what does this arrow mean. Then another important requirement is that for any three arrows, they are associative. So F composition G and then composition H equals to F composition G composition H. This is quite natural property. So you can think about arrows like if there is an arrow between two objects, you can travel from one object to another. And if there is a path from one object to another and then to one more object, it doesn't really matter how do we travel, how do we group this kind of movement along arrows. So this is useful. And also there are rules for compositions. So compositions, they are kind of identity functions in a sense that they do not change underlying objects. So if there is a arrow F, then F composition IDA is the same as F, and IDB composition F is the same as F. So if we move from A to B, and then we use this identity arrow, we still stay in B, we do not go anywhere else. So all of those properties, they are very natural properties. And that is exactly what makes categories useful in practice, because practical objects in real life, they usually obey those natural properties. And to illustrate some of the concepts, we use diagrams similar to those shown here on the slide. Those two diagrams, they show the last property of identity function. So suppose there is a mapping F from A to B, and this mapping F from A to B is identical to composition of identity function, which maps from A to A, and then function F from A to B. So this is this diagram represents this first equality. And similarly, the second one, which shows that if we move from A to B, it's the same as moving first to B and then applying identity function. You can, by the way, notice that in category theory, usually we write composition in the reverse order. So F composition G means that G is applied first and then F is applied. Okay, so what are practical examples of categories? Well, we can think about like simplest examples, like category of one object, like we can have one object and no arrows, or we can have one object, well, no arrows we cannot have, we can have one object and identity arrow. Then every graph has underlying category, because as I said, categories, they are broader than graphs, but graphs can be considered to be categories. Any order relation can be considered to be a category. So if we have the partial order or we have complete order on some set, so if order is a set A with the order relation, something like this, a pair like this. So this order relation can be interpreted as arrows. So if let's say 3 is less than 5, we can say 3 arrow 5, and this would be arrow 7, and then 6 would be less than 5, sorry, more than 5, and 6 would be more than 5, and 7 would be more than 6. So the arrows would go like this. So any ordered set can be interpreted as category. And then we move to more interesting categories, like we can start talking about category of all sets. So like objects would be sets. So for example, set of integer numbers can be an object in the category. And if sets are objects, then arrows between them naturally would correspond to functions, right? So for example, if we have a set of integer numbers, like 0, 1, 2, 3, 4, and so on, and I have a function which multiplies the argument by 2, then it would map to another object, which would be even numbers, right? So it would be 0, 2, 4, and so on. So you can say that this function corresponds to mapping between the set of integers and set of even numbers. Of course, there would be a lot of functions which map from integers to integers. For example, function +1, function +2, which just adds a number. It would map the set of integer to integer. So category of all sets looks like very promising and useful to us. And we will deal today almost entirely with a category very similar to this category of sets, which is called category of all types in the functional programming language. It can be slightly different from category of sets because, well, we include also functions here, so of all types and functions. And also there are some small mathematical differences. For example, it is difficult to discuss functions in a programming language because a function in the programming language can be a non-terminating function. So, for example, if I write the infinitely recursive function, like it would not return anything, it would not terminate. And taking such functions into account requires us to provide some more mathematical clarity. So, for example, to introduce a special value for non-termination or doing things like that. But let us not go into a lot of detail, a lot of mathematical detail. So we will today consider this category where objects would be types of functional programming language and arrows between objects would be functions which map one type to another. Okay, so let me introduce a few more useful concepts. And another concept is opposite category. So if there is a category K, so suppose a category K has objects A and B and an arrow F between A and B. So for this category, we can automatically introduce a dual category or opposite category where the direction of an arrow is reversed. So the dual category would consist of the same objects, that would be A and B, but the arrow F would be reversed. That is just a very natural concept. Naturally, we can prove that if we reverse all arrows, the rules of composition would be preserved. So for every morphism F from A to B in the category K, there would be a morphism from B to A in the morphisms of opposite category K op. So why this concept is useful? Because it allows us to see the duality between some of the definitions. And let me show an example. There is something called initial and terminal objects, because some categories can have those initial and terminal objects. And an object is called an initial object if all arrows from this object go to other objects in the category. So suppose there is something like A, B, and C, and then there is this initial object I. For initial objects, there has to be one and exactly one arrow which goes from this object to all other objects in the category. So one and only one arrow. And an opposite notion is terminal object. Terminal object is, let me call it T, is an object which has one and exactly one arrow going from all objects in the category to these terminal objects. So let us think what can be initial and terminal objects in the category of types. So let's first consider the terminal object. So terminal object, it has to be like for any type, there has to be only one function from this type to this terminal type. So suppose the terminal type would contain, for example, two values. Like it's a finite set with two values. In this case, like for example, functions from integer to this terminal type, there would be plenty of those functions, right? Many possibilities. So the only way to have just exactly one function is to have this terminal type consist of only one value, right? So, like, suppose that this terminal type contains only one value 5. In this case, like, there can be only one function from integer to this type, which always returns 5. And from string to this type, it also has to always return 5, right? So terminal object can be any type which consists of only one value. And there can be many terminal objects. So we can say that those terminal objects are unique. So we want to be able to talk about one terminal object. And all terminal objects which have exactly one element, they are kind of very similar in structure between themselves. So we don't need to like distinguish between them when we start like proving some mathematical properties. So that's why we can say that terminal objects, they can be many of them, but they are unique up to isomorphism. So there is one-to-one correspondence, like if there is a terminal type which contains only one value 5, or terminal type which contains only value 6, they are different, but they are very similar structurally. So we can say a terminal type in this category of types would be a type containing only one value. So up to isomorphism, it is unique. And normally in programming language like F#, we denote some kind of special value and special type to be this terminal type, and it is in F#, it is called unit. And the value of type unit is denoted normally like by those two brackets. So we can say for any type there is a function unit from big U with big U, which takes any argument and returns this predefined value with two brackets. So this terminal type is exactly type unit in F#. And when functions return unit, and you know that functions which do nothing, they typically return unit, those functions literally they return this terminal type. So if terminal type is unit, then what is initial type? And by the way, in C++, in programming language like C++ and C#, there is also terminal type, and it is called void. Void type in C++, even though there is no specific denoted value which is returned, but in fact it is a terminal type. And what is initial type? Initial type, there should be exactly one function from this type to any other type. And if we take like the type with one element would not be valid here, because I can build a function which maps from, so for example, from this one value type to integer, for example, there could be a function which returns always 5 or always 6 or always 7, and there would be different functions, but I need only one function from this type to any other type. So the only possibility is to for this initial type is to be an empty set. So I cannot actually build any useful function which returns a value. So this type in languages like Haskell, it's called void with big V. In F# there is no specific type for initial type, and the function which takes void and returns, well, it doesn't return anything, but this function is called absurd. And coming back to the notion of opposite categories and duality, you can probably understand that if we take opposite category, then initial type of original category becomes terminal type in the opposite category, and vice versa. Okay, so that was some short introduction to category theory. Now let's move to something more practical and more useful, namely the notion of functors. So functors are mappings between categories. So if there is a category C with objects A and B and some arrows, for example, arrow F between A and B, and I want to map it to some other category. So this functor would be denoted by big F. So it means that I map the object A to some another object f of A, big F of A. I map the object B to some object f of B. And I also want to be able to map arrows, right? So I map arrow f to some arrow big F of small f. And this mapping would be called functor if it preserves some important quantities. So speaking more formally, I say that functor f is a mapping from category key 1 to category key 2 if this f maps all objects of category key 1 to all objects in category key 2 and all morphisms in category key 1 to all morphisms in category key 2. But it should first preserve the identity functions, right? So if I map the identity function in the original category, it would be mapped to identity functor in category in the category K2. So f of id A would be id of f of A. If there is a morphism from A to B, then there is always a morphism from f of A to f of B, and it also should preserve composition, right? So if I take the function f composition g, it's the same as I apply big F to F, big F to G, and then composition in the category K2. So a very natural thing to ask from functor. So what's the practical examples of functors? Well, in F#, let's consider this example. I want to be able to operate safely on some integer values, but some operations, they can fail. So if operation on integer number fails, then if I want to deal with those kind of failed operations, I need to use optional type. Optional type is, I remind you, it's either sum of something or none. So it's like two-valued data type, so it can be either none or sum of 10, for example. So I want to be able to operate on those option types. And I want to be able to apply normal functions on integers to this kind of safe type. So how do I do that? Suppose I want to add to apply the function +1 to this option type. So in this case, what I can do, I can introduce another function fmap. This fmap would be, it would actually be a functor. And so actually, let me take a step back and show you what happens here. So I have the integer type in my category of types. So integer type contains a lot of functions which operate on integers. For example, function +1. Right. So let this be a function +1. I want to be able to start operating in the domain of optional integers. So this option of int, it's another type which contains sum of integers or the value none. So what I want to be able to do, I want to be able to use the function which corresponds to this +1, but in the domain of option types. So this is what I do. I call this functor. I'd say, okay, the functor f would map all integers to this option type, and the functor f would also map the functions. So in F# I cannot use the same symbol f to map both things, types and functions. So for types I would use this sum of x, and for mapping functions I would use the function called fmap. So if I say fmap +1, it gives me a function which operates in the domain of option types. So if I say fmap +1 applied to sum of 10, it would return me sum of 11. If I say fmap +1 applied to none, it would return me none. Right. So here is the definition of this fmap function. So it's fmap of f. It looks inside this option value. If it's none, it returns none. If it's sum of x, it returns sum of f of x. And for simplicity, I can also like introduce this notation. I can define the operator dollar f of x, which use f map of f applied to x. In this case, I can write +1 applied to sum of 10, and it would automatically use f map behind the scenes to do the operation on option type. So this is quite useful actually, because I can build sort of composition of those functions, and they would like be naturally composable. So why is this useful in practice? Consider a normal example, like if in C#, for example, I want to write some code. I have an ID of an employee. I want to get this employee by ID from some database, and then I want to return the name of this employee. So I basically want to define the function something like get name by ID. So how do I normally do that? I call the function get employee by ID, and then like what happens is that if the ID doesn't exist in the database, the function would typically return something like null or none or something like that. And I would need to check if employee is not null, then I can return employee.name. Otherwise, I need to return null as an indicator that the function gave an error. So this looks like a lot of code, and I can encapsulate all of that inside fmap. I can say, suppose I have the function get name, which returns name from employee ID. I can say I want to return fmap get name from get employee by ID 42. And in this case, this function get name assumes that name always exists. Then it's not null, because like that is the way it works. Fmap only calls this function if the value exists. And this code is definitely more compact than the code on the top. That shows you how you can use the notion of functors even in traditional programming languages. What are other examples of functors? So lists are also can be considered functors. Let's say I have integers, I have strings, I have two types, and then I have the function, for example, which maps from string to integer, something like length of string, right? So, and if I move to the domain of lists, I can say, okay, I can have this list functor, which maps list integers to list of integers, and it maps strings to list of strings. And naturally, I can map this function len to the domain of lists. And this would be exactly list.map from len. And this is why this function is called fmap, because in lists, this function is called map. I can also imagine that trees can have the same kind of properties. I can have mapping function which maps one tree to the other, applying any arbitrary function f to all leaf values. And that would also be a good example of a functor from one category to another. Actually, when we were talking about lists and option type, I said it maps one category to another, but in fact, we are mapping from category of types to the same category of types, right? Because the option type is also within the domain of all types of a programming language. And I can also say that, okay, the list functor, for example, maps integer to list of integers, but I can then map list of integers to the list of integers. So I can apply the same functor again to produce like more complex structures. So in fact, all those functors I have been giving you as examples, they map category of types to the same category of types. And those functors which map category into itself, they are called end functors. This is just a useful terminology to know. And normally, like when we say functors, we mean end functors because we are always consider just one category of types in our all examples in our when we talk about programming languages. So once we start talking about functors, of course, we can say this that this functor operation kind of forms the category in itself, and we can start talking about composition of functors as well. So, for example, if I have this original category C with objects A and B, I can apply the functor F, which would map it to category D. And then I can apply another functor G, which maps category D to another category E. And because all the functors preserve compositions, I can talk about composition of functors F and G. In practical terms, you can first consider moving from integer to optional type of integers, and then you can build lists from that, right? And that would be an example of composition of two functors. Okay, let us come back to the demonstration of optional functor. And I have already mentioned that we can map, we can build this fmap function for optional type. And now I can say, for example, I want to take the function +1, and I want to apply it to some optional value, sum of 10. And it would give me, as a result, sum of 11. And if I apply this to none, it would give me none as a result. That sounds good. But what if I want to apply the function in the carried way? So here +1 was a function from integer to integer. But what if I want just to take the function plus and apply it to two optional integers, like, for example, sum of 10 and sum of 11, and that doesn't seem to work correctly. It gives me a type error. Why does that happen? Let's just apply plus to sum of 10. That works correctly, but look at the type. It gives me the optional integer to integer function. Due to the nature of how this function is implemented, once I applied the carried function to the optional argument, it returns me this optional result. So now if I want to apply it again to an integer number, I need to unmap it to a normal function. So what I want to do here, I can say, okay, I want to take the value here. Now I can apply it to sum of 11. And this would give me sum of 21. But that definitely looks ugly, right? I don't want to be writing something like this. So what I can do, I can produce another operator. So let me produce this operator star, which would take both optional function and optional argument. So it would take f and x. And what I will do here, I will match it. So let me say it match fx with, and I will consider several options. So f is none. If the function is none, then I would return none. If the argument is none, I would return none. And if both function and argument are exists, so if it is sum ff sum xx, I would return sum of ff applied to xx. So this star would take functored, like optional function and optional argument. And now instead of using $, I just replace it with this star, and it gives me the result. Let me define this. I'm sorry, the problem is that I have forgot to put brackets here, because if I define the operator, I need to put brackets. So let me do this again. Now I can apply plus to 10 and to 11 like this in the beautiful way. Well, not really very beautiful, because it looks very asymmetric, right? I use first $sign to compose the function with first argument, and then I use this another form to do the second application. So I want to be able to write something like this, which is kind of symmetric way, but it gives me type error. Why? Because my first function is not embedded in the functor type. So I need to put here sum of plus. And now this looks like very symmetric form of applying optional function to optional arguments. In fact, what I can do, I can define this as a function called pure f equals sum of f. And here I would use the word pure. This looks like a very small change, but it just gives me well, a nice way to say that this plus, this optional plus, is so-called an applicative functor. So what is an applicative functor? An applicative functor is a functor which transfers values to the functor domain, but we also transfer functions to this functor domain using the constructor pure. So if we talk about applicative functors, we have the constructor pure, and we have this operator star, which allows us to compose functored function with functored arguments. And so applicative functors, they are a way to use multifunction arguments in the functor domain. And using up optional types is just one example. Of course, we can use it with other functors as well. Suppose I want to use it with lists. So what would be the list form of applicative functor? Well, the function pure would construct from any function a list of one element. And what would be the meaning of this star operator? Well, it would say I want to apply every function in this left list to every argument in this right list and produce the list of all possible combinations. How would this be implemented? Well, I would first map and apply all functions in this first list ff to my original list LL, and then I will concatenate all results into one big list. So let me show you how this works. So I have put this code into my VS Code, and now let's experiment. So I want just to use simple addition. So I want to add 1. Let's say I want to add 2 plus 3. So I would say here plus, pure plus, and then 2, and then 3. So that should be, oops. So sorry, plus should be definitely in brackets. And without list, because pure takes just one function. Okay, so this gives me 5. So if I want to say I want to add 2 and either 3 or 4, what would it give me? It would give me 5 or 6. So I say if I want to add 1 or 2 plus 3 or 4, it would give me 4, 5, 5 or 6. And then I say, what if I want not only to add but also to multiply? In this case, I can put here a list of operations, and it would give me all possible additions and multiplications across all those lists. So you see, we now have defined a functor which allows us to raise arithmetical operations, actually any functions, to the domain of lists, and it corresponds to so-called non-deterministic computations, right? It can be either this or that or different other options. Now let us see how this can be applied to a practical task, and the task would be a small logical problem. You probably know that what is so-called lucky bus ticket. In Russia, in the buses, they used to give you the tickets with 6 digits. So it would have a number like 1, 3, 7, 6, 0, 4, for example. So this would be like the number of a bus ticket. And people like would do like they would calculate the sum of first 3 digits, sum of last 3 digits, and if they are equal, in this case 6 plus 4 is 10, and here 7 plus 3 is 10, and plus 1 is 11, so it is not a lucky ticket. And if it was like 0 here, for example, it would be called a lucky ticket, because the sum of first 3 elements and the sum of last 3 elements is exactly the same. This was a small exercise that parents gave to their children on the bus, so that children learn how to add numbers quickly. But what we can do, like if we feel sorry that our ticket is almost always not a lucky one, we can define something called a weekly lucky ticket. And weekly lucky ticket, it would like turn almost any ticket to a lucky one, but it would also require us to do more complex computations. So a weekly lucky ticket, we would consider breaking up the ticket into 2 parts, and like in any possible way. And then we want to build any arithmetic expression from the left-hand side and any arithmetic expression from the right-hand side to make the numbers equal. So for example, we can say in this case 0 times 3 plus 7 plus 6, and the right-hand side we can say 0 times 4. Both would be equal to 0, so this ticket is weakly lucky. So what we want to do, we want to be able to split the ticket into 2 parts and to construct all possible arithmetic expressions from its digits. So definitely the most complex part here is constructing all possible arithmetic expressions from the given digits. And how do we do that? To do that, it's not enough just to for example, let's say I want to take the first element of the list and then combine all possible arithmetic expressions from the right-hand side and then combine it. Because arithmetic expressions, they are not like lists, they are not linear trees. We need to be able to, for example, to make left-hand side expression something like 0 plus 3 times 7 plus 6. So in this case, what I want to do, I want to split this list between like in 2 parts and put all possible operators in between them. So to produce this kind of all possible arithmetic expressions from the numbers in the list, I need to be able to split the list into 2 arbitrary parts, right? So we will start by defining this function called split. So the function called split would take a list and split it into all possible ways. So let me show you how it works. So I would say, for example, split 1, 2, 3, 4. And it would give me pairs, a list of pairs, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. And it would not give me empty lists. So how does this function work? For a list of 1 element, I return an empty list because I cannot split a list of 1 element into 2 halves. If the list is not empty, if it's head and tail, so first I return the most obvious split. The head is the first element and then the tail. And then I do recursive call. I split the tail. And splitting the tail gives me several options, right? So I have a list of options how to split the tail. And what I need to do, I need to put the original head to all possible elements in this list of possible options, right? So that is how split works. So now what I need to do, I need to be able, like if I have the numbers 1, 2, 3, 4, I need to be able to compute all possible expressions by splitting this list. So let me define the function. I would call it ops. Let ops a and b. A and b would be 2 parts of the list. And I would say, okay, I want to take operations plus, minus, and multiplication. I would not consider division here because it would give us division by 0. I want to apply it to all possible values in A and all possible values in B. So this would be my ops operation. So if I say I want to compute ops of 1, 2, 3, 4, so it would give me all possible values that can be obtained by combining 1, 2, and 3, 4. Like 1, 2 are all possible values for A, 3, 4 are possible values for B, and if I combine them using all possible operations, it would give me the list of possible values. Okay, now let me define the main function for my task. I would call it values, and it would take a list. So if the list is empty, then I would return empty list. If the list is just one value of x, then all possible values are just x. And then if the list is anything, if something else, what do? I take this list, I split it into all possible combinations of two sub-expressions. Then for each sub-expression, let me call a list map. And this list map would go through all possible combinations where A and B are left-hand side. So, and then I use my function ops to combine all possible values that I can obtain from the left-hand side of the list and all possible values that I can obtain from the right-hand side of the list, B. So this gives me the big list of lists of possibilities. So what I do then, I can concat all those possibilities together, and then I can call list.distinct to get rid of all possible duplicates. So that is my function that gives me all possible combinations for the list of values. So I can say values 1, 2, 3, and it gives me all possible values that I can get by combining numbers 1, 2, and 3 together using all possible arithmetic operations. And from that, of course, it's pretty easy to define the function that would check if I can split the list into two parts with equal values. You can use the same function split that we have defined earlier, and then compute all possible values for the left-hand side split, right-hand side split, and see if those two sets intersect. So I would leave this to you as a simple exercise to finish this problem. Let us come back to the notion of category and talk a little bit more about theory. And we will introduce two notions of products and coproducts. In fact, it is a different way to define the notion of pair and algebraic sum using category theory. So how can we do that? We need to be able to define the notion of pair without explicitly constructing it from parts. So this is done in the following way. We can say that there is a product A times B for any objects A and B from the category K. This is also an object called C. And this object contains two special arrows, which are called projections. FST, which maps from C to A, and SND, which maps from C to B. So, in fact, this object pair can be decomposed using projections into two different objects A and B. So, suppose I remind you that we consider category to be a category of types. So, A, B, and C are types. So, if C, for example, is a pair of integer and string, then projection 1 maps from this pair to integer, and projection 2 maps from this pair to string. So if we leave the definition at this point, it does not contain any requirement that those functions allow us to represent the pair fully. For example, I can define the projection which maps from any object to number 5, for example, right? From any tuple integer times string to the number called 5, and this would obey this definition. So I also need to add some kind of additional requirement that this pair can be fully reconstructed by combining back those two projected values. So this is added in the following way. We say that also that for any object D, which maps back to original projections A and B, there is only one possible arrow which maps from D to C, which is to say that C is fully defined by A and B, right? So you see, we define pair by looking at the way this pair can be deconstructed into two parts. And in terms of set, this definition corresponds to Descartes' product, A times B. In terms of our category types, it corresponds to the definition of tuple. So product allows us to define tuples on types. And naturally, if we have definition of pair, we can consider opposite categories. So we can reverse arrows in the other direction, and this gives us the definition of so-called coproduct. In category theory, many definitions can be reformulated in terms of opposite category, and they are called something. So in this case, coproduct, or it actually can be called sum. And a sum of A and B is so in this case we have arrows following in the opposite directions, and the functions, they are called not projections, but they are called injections. So now we have two injections which allows us to construct this object C from the object A. So if it's a sum of integer and string, so we can construct an object from an integer, or we can construct an object from string. And again, this construction works in such a way that this construction is unique. So in terms of set category, that gives us the direct sum of A and B. In terms of category of types, it gives us the union type. So it gives us int of 5 or string of hello, something like this. So those injection functions, they are in fact constructors of this type. So once we have defined sums and products, we can build complex data types from them. This is something we have already discussed, but let me again reiterate this idea of algebraic data types. Why they are called algebraic? Because product and sum, they can be considered as basic arithmetic operations, and by using them we can combine different types together. And those arithmetic expressions which correspond to those types, they would obey the same properties like distributive law, commutativity, and so on. So let me give you some examples. So suppose what can correspond to the type void? Type void or empty set, it has no elements. So naturally it can correspond to the number 0. Now type unit, which consists of only one value, can correspond to number 1. Then sum A plus B, it's basically two different it is the value which can contain two different types, and we can use, for example, this definition either AB, which is, for example, left of A, or right of B, and this would be denoted by A plus B. A times B would be a tuple AB, a type consisting of two subtypes. Then, for example, if I have the type Boolean, which is either true or false, we can say this is true or false is 1 plus 1. Or is the sum, right? So 1 plus 1 is 2. So that kind of means that type Boolean contains two possible values. If I have option type, it is defined as none or sum of t. So none is the type which consists of one value, and sum of t is the type which is denoted by some letter A. So it corresponds to the expression 1 plus A, and so on. So we can say that any expression of this form has some kind of underlying data type consisting of sum or product. Now let us see how the arithmetic laws would work. So 0 times A is 0. So that also holds, because if I construct the type with empty set in it, it doesn't allow me to create such values. So it would also have 0 elements in this kind of data type. 1 times A gives me a tuple of unit type and the value of type A, which also doesn't give me anything new, just the original type A. So 1 times A would be equal to A. Now, going to the more difficult things, A times B plus C. What would correspond to A times B plus C? It would be a tuple, right? This tuple, it's either A or left B, or it is a tuple of left, and then this type B plus C, left B or right C. If we apply the distributivity law, it would be A times B plus A times C. So we can say it is the same as saying it would be a sum of A times B, and A times B is left of tuples A and B. And with A times C is the right of tuples A times C. So instead of, so in the first case, I would be writing something like 3 and int 4, if we consider tuple to be integer or string. In the second case, I would be writing something like int of 3 times 4, of 3 and 4, int of tuple. And it is those two things, they are structurally identical. So in this way, we can say that this law actually is applicable, it actually works. Now going to more interesting things. When I define something like lists, right, I can say that list of T is either empty list or a constructor of T and list of T. So it's a kind of recursive definition of types. And if we write an expression similar to the one here, it would be x equals 1 plus T times x. Not really clear what it means, but what I can do, I can say, okay, x equals 1 plus T times x. I can put here, instead of x, 1 plus T times x. So I can say x equals 1 plus T times 1 plus T times x. And it would give me 1 plus T times x. And if I do it infinitely many times, what I would get that x equals 1 plus T times T plus T times T times T plus T times T times T times T times T, and so on infinitely many times. And so it corresponds to the intuition that what is a list? List is either tuple of length 0, which is represented by 1, an empty list, or one value of type T, which is represented by T, or tuple of 2 values of times T, or tuple of 3 values of times T, and so on. So you see, by like expanding this recursive definition into this infinite sum, we can get the definition that what list actually is. It is actually a collection of tuples of different sizes. Although you cannot, of course, represent this infinite sum type, but at least you can see that like manipulating expressions, algebraic expressions, lead us to the same structure, the same structures in terms of types. Okay, now let us move to one more structure. We have talked about functors, we have talked about applicative functors, which allow us to move values to a different domain. Now let's talk about monads. Monads, first let me give you some intuition. So intuition is pretty similar to functors and applicative functors. I want to be able to build kind of chains of operations, and the operations can either be successful or not successful. And for example, if operation is successful, for example, function good of x, what it does, it increases the number by 1 and returns sum of x plus 1. If the operation is bad, it gives me none. It represents that the operation is bad. So if I have the chains of those operations, anything can go wrong at any time. So if I start with sum 1, I want to be able to chain it to a good function and get a good result, sum of 2. So because good function increases the value by 1. If I start with sum 1 and I give it to bad function gives me bad result for any x, I want to get the bad result, none. But if I want to apply the functions in a chain, I want to start with 1, then apply the bad function, and then apply a good function. And still, like, I don't want to be getting any errors. I want this to peacefully return me bad result, none. So the idea of monads is to be able to chain operations together, preserving some kind of additional state of the operation. So if the operation failed at some point, I want to be able to take this state up to the end of the computation. So how this is implemented in terms of types and structures? For any type T, I want to define so-called monadic type, M of T. So this is M of T. And the functions which I am applying to this monadic type, they take underlying type T and return monadic type. So when I say the operation can go wrong, it means that I always start with some kind of good result. So this function f starts with a good result. So this, for example, function good of x, it takes an integer x. So it's not an option type, it's an integer. I have the good result as an input, but it can go wrong. So I can return either sum or none. So I return monadic type with some additional state. And but I want to chain the operations together. So in my chain, all values are monadic. So you see, I start with like monadic additional value option type. And then I chain it to the function, to one function, to second, to another function, to another function. So any function accepts normal result and returns the monadic result. And the function to bind values together is called bind. Actually, this function, which I denoted here by arrow equals, it is the traditional way in Haskell, for example, to denote this operation. It is called bind, and I bind monadic input to a good operation and produce again the monadic input. And then I want to be able to bind it to some more functions and form a longer chain. So let me give you an example, like very simple and stupid example. I want to implement a plus b in console, but when somebody types a value, he can type something wrongly. So what I do here, I print like the prompt, then I do console read line, and then I try to convert this value to integer. If it doesn't work, I return none. If it works, I return sum of integer s. And I want to read two numbers and return the result. And if somebody types something except a number, I want to just to say none. So what can I do to write it nicely? Of course, I can do a lot of if checks. I can say I want to read one number, then if it is none, then I return none. Otherwise, I want to read the second number. If I read the second number and it is none, I want to return none. Otherwise, I want to return a plus b. And that is like tedious, a lot of ifs. What I can do, I can write if, I can put if inside this monadic bind. So I say this bind. So bind takes a monadic value and a good function. So what I do, I check the monadic value. So if it's none, I return none. I don't even start applying the function f. And otherwise, if it's not none, I apply a function f to a dot value. So I unpack the value from monad. I take a good value which is inside it, and I apply the function f. So if I want now to compute a plus b, what do I do is the following. I read the function, I read the number, then I do bind, and inside bind, I assume that the function, this kind of function has some good value x. So what I do next, I read the second value inside this function, and I bind it to another function which assumes that I get the good value y, and I return sum of x plus y. So if somebody typed something wrong in the first place here, this function f would not be called at all. So it would not even ask me for the second value. If somebody typed a good value here, then this function would invoke another read, and another read would read another number, and then if the number was good, it would invoke this function which would return me the sum. Otherwise, it would not read the second number. So it would be exactly the same as writing a lot of ifs, but like something like this. You see, very long and tedious code. Let a equals read. If a is not none, then let b equals read. If b is not none, then print something, then else print bad input, and so on. So instead of writing this big code, I write just a chain of computations. So that is the idea behind monads. Let me give you another example. Monad doesn't have to be an optional value. Monad can be anything. Like monad can be, for example, a monad of non-deterministic computations. Let's say, let us assume the following problem. Vasya was born in the year 2000. So if he was born in the year 2000, that means that he is 25 or 26 years old. His brother Petya is 2 or 3 times older than him, and his sister Lena is 1 year older than Petya. How old can Lena be? So how can we solve it? We can say, okay, our monad of non-deterministic computations, it's a monad around integer type, right? Because I am talking about age. But because Petya can be either 25 or 26, it can be represented as a list of possible values. Okay, so what would be the bind operations in this case? Bind operations would take a good non-monadic value. So assume I know that Petya is 25. So not Petya, but Vasya is 25, right? And Petya is 2 or 3 times older than him. So I take this age of 25 and I produce all possible combinations from it. So 2 times 25 or 3 times 25. And my bind, what it has to do, it has to take all possible values from the monad, and for each value, it has to apply the operations, right? So for 25, it multiplies by 2 or by 3, and for 26, it multiplies by 2 or by 3. So what it means that essentially I need to do list.collect. List.collect is actually map and then concat. You can implement it by 2 functions. First, map function f to all input values, and then collect them and produce one list. So if I want to formulate my problem now, what I can say, I can use the following syntax. I can say I start with 25 or 26, then I bind to the function which multiplies by 2 or by 3, and then I bind it to the function which gives me for x plus 1, because Lena is 1 year older than Petya. And this gives me the list of possible values of the age for Lena. In fact, for monads, I can say I need to define the following operations. Operation called return, which produces from some value x, monadic version of x, in this case, the list of one value of x. Or I can also introduce, like for symmetry operation, return prime, which already takes the monadic value. So in this case, my final solution would be, okay, I want to start with monadic value. If I started with just one value, I would say return 25, for example. Here I say, okay, I start with monadic value. Then I bind it with a function which for any x returns the monadic value x times 2 or x times 3. And then I bind it to the function which for x returns the value x plus 1. So why do I need this return? It kind of hides inside the notion of the monad. I don't need to remember that the monad is a list. So that is an example. Let us come back to the theory and talk about how this is implemented theoretically. Theoretically, it turns out to be easier to use another operation instead of bind operation, which is called fish operator, and it looks like this: fish operator. Fish operator is easier to understand because it is kind of symmetric. Because monadic operator is it takes like on the left hand side it takes a monad, on the right hand side it takes the function from good value to monadic value. So Claesley fish operator takes one function from a to m of b. So it's a kind of function which accepts a good value and returns monadic value. And then it takes another function which takes good value b and returns monadic value of type c. And then it basically composes them together. So from a to m of b, from b to m of c, it gives me the function from a to m of c directly. So it is essentially a composition operator, right? So if you see the difference here, f is a function from good value to monadic value. So here a blue box means monadic value. G is from b to monadic value c, and fish operator composes that into one. While the bind operator on the right, it takes the monadic value b, function from b to c, g, and it binds monadic value b to the function g. So in bind, you see on the left hand side we have monadic value, on the right hand side we have function. In fish operator, on both right and left hand side we have functions. And the category which has this fish operator is called Claesley category. And so I just remind you what we have learned so far. We have learned about simple functors. Simple functors, they are defined by one operation fmap. Then we have learned about applicative functors, where we have operator star and the operator pure, which uplifts the function to the functor space. And in monads, we have two operations. We have operation return, which returns a monadic type, and we have one of those operations. Well, why do I say one of those? Because they can be defined in terms of each other. We can essentially need to define just one of them, either bind operator or Claesley fish operator. Well, for monads to be a monad, it also needs to obey some structural laws. Why? Well, for the same reason as functor needs to obey functor laws, to be respectful to composition, to be respectful to identity functions, and so on. So what are monadic laws? In terms of fish operator, they are very easy to understand. So I remind you that return function, what it does, it takes a value and produces the monadic variation of the same value. So if I take this function return, which essentially does nothing, and combine it with the function f, I need to get the same function f. If I take function f and combine it on the right-hand side with the return operator, I need to get the same function f. And also, this fish operator has to be associative. So if I combine f and g together and then combine it with h, it is the same as if I combine g and h together and then I combine it with f. And those are pretty natural algebraic laws. So they are easy to remember. And you may have heard, that monads are something which people use to scare people out of functional programming. And they say monads are very simple. They are just monoids in the category of n the functors. And this is exactly why, because those laws, they are in fact definition of the structure called monoid. Monoid in the algebra is an operation, is a set which contains one operator which is associative and has some identity value which is called 0 in monoid. So in here, return is this kind of 0 or identical value which does nothing, and monoid operation is this fish operator in the Claesley category. Why is it called in the category of n the functors? Because monad is an n the functor, because monad maps from all types of functional programming language to the same category of types. If we instead of fish operator want to formulate the same laws with bind operator, it becomes kind of less beautiful, because we need it becomes like much less symmetric and much more difficult to remember. We say return of x bind f is the same as f of x. If I say some monadic value bind return is the same as monadic value, and then if I say monadic value bind with f and then bind with g, it is the same as I take monadic value, then I bind it with the function from x to f of x bind g. So you see this kind of law, it is simple associative law when I formulate it in terms of fish operator, and it becomes ugly if I formulate it otherwise in terms of bind. Why do I need monads? And should monads scare you away of functional programming? Well, actually, no, because monads are introduced to make life simpler, actually. So in F#, for example, monads, they support special syntax. You can define your own monads and you can embed them into the syntax of a programming language. So, for example, for non-deterministic computations with Vasya and Petya and Lena, I can write the same code using very simple syntax. I can introduce, and I will show you in a moment how to do that. I can introduce this special kind of syntactical construction, non-det, and I can say, okay, result is non-det, and then I can say let exclamation mark Vasya equals to 25 or 26. Let exclamation mark Petya equals to 2 times Vasya or 3 times Vasya, and let Lena equals Petya plus 1, and then return Lena. What does it mean, let exclamation mark? Let exclamation mark means that I want to bind this Vasya to a monadic value. Let without exclamation mark, for example, Lena, means that I want to bind it to normal deterministic value. And when I write this non-det, in fact, it would return me a combination of bind operators, and I need to specify which bind operators. And this is done by creating this kind of builder. So this is kind of a little bit complicated code, but not very much. I say I want to define a class non-det builder with operations return, which is ret x, and ret x, I remind you, just returns the list. Return from is an operation which returns the monadic value without any changes, and bind is the bind operation which we have defined earlier for this specific non-deterministic computation scenario. Then what do? I define the variable non-det, which is non-det builder. And once I have executed this code before this workflow, I can start using non-det as the syntactic constructor of the language. And this would be mapped to this kind of chain in the computation. So you see, in the beginning here, because I say let exclamation mark Vasya, it invokes my function return from. Then when I say let exclamation mark Petya, it again invokes this function return from, and then when I use Lena, it invokes the function return, and between them it puts the function bind. So I can control in this computational workflow, I can control which functions are inserted between each line of this code. I can define it myself, and this allows me to create some extensions for the programming language. So you just need to define this class. In addition to simple return and bind, it can contain also some other values, like 0, for example. 0 allows me to introduce the value which would be automatically returned if I do not explicitly specify the return statement. And then I create the instance and I can start using it. Let us discuss one good example of a monad, which is called state monad. And let me start with an example. Suppose I have a tree of numbers. I would define the type tree, which is either nil or a node with 2 subnodes, and some kind of tree consisting of numbers like 0, 1, 2, 3, and so on. And suppose I would just want to print all elements of a tree. This is a simple exercise. I just say I want to match the tree. If it's nil, I do nothing. If it's some kind of node, I print the left-hand side first, then I print the current number, and then I print the right-hand side. And if I run this, it gives me 1032. Now, suppose I want to simplify this code just a little bit. I want to print a number in front of any element. Like I want to print the numbered list 1, 2, 3, 4, 5, and then the value. why is this a little bit complex to implement? Because I need to keep track of this kind of state. I need to pass this number along as an argument to my function. So I want, let's say I want this, I need to add another number n here, and then I want to say, okay, if it's not XLR, I want to print left hand side, but I need to remember, like I need to print to pass n here, and then I need to remember the value which is returned, n1, and then I want to print this number n1, but n1 plus 1 because I need to increment it, right? And then I need to return the value of print r n plus 2, right? So I need to write the code like this. Just here x is here. Something like this, I think. Yeah, the only problem here is type conversion. So now with nil, I need to return n. Okay, now it becomes good. I execute this, and I want to print t, and I pass the initial value 1, and it gives me, well, it starts here with 2, so I need to start with 0. So 1, 3, 3, 5. So what do I do wrong here? So I need to say here n1 plus 2 probably, not n. One, 3, 5, 7. And 1 plus 1. You see, a little bit difficult to troubleshoot. 1, 2, 3, 4. Okay, now I have succeeded, right? I have changed my function, and it works perfectly, but I need to be like careful. I need to always remember to pass this value of the state around, and in some cases the state can be a little bit more complex than just one value. So how do I monadize this code? How do I make it so that I don't need to change the code a lot and the logic a lot? I don't need to explicitly pass an extra variable, but still somehow use this state. This can be done with the idea of monads. So idea of monads of the state monad is the following. I replace the function with a function which accepts always a state as the first argument, and then returns a state as well. So bind would take this monadic state and produce another function which takes state as 0. It executes s on state as 0, and in return some value, it gets as the result some value a and then some new state s, and then it executes the function f on the value a of the result of x and new state s. You see, so this is how the bind operation in monadic world works. And if I want to return something, return in this monad, return s of a would be returning a function which takes a state and returns a pair of the value a and this state. So you see, like if any function would always return a pair in this world. So now what I need to make it easier to use in F#, I define a state builder. And the state builder consists of the function 0, which is return s function, return, which return s of a, and bind, which is x bind f. And I introduce the word state to make it easier to operate on states. And then I introduce two functions for simplicity. The function called getState. You see, it returns as the first value of the pair, it returns the value of the state s. I introduce the function setState, which ignores the input state and inserts any value s into the state. And execute is just an auxiliary function to simplify things. So let me show you how this state monad can be used. I take original function without extra argument, and I just surround it with the state, my new state keyword, which I have introduced. Right? I say it is a state, and inside this, I can do some things, some interesting things. So because print is now a monadic operation, I cannot just say print L, I need to say do print L. Do is a kind of let exclamation mark which ignores the result. And because my function returns unit, I just need to ignore this unit. So I say do exclamation mark print L. And the same for the right hand side. I say do exclamation mark print R. What else? Now to print the number n, I need to get it from the state. So this value n, which I would print here, I get from the state. So I say let exclamation mark equals get state. Then I use this for printing, and then I say do exclamation mark set state n plus 1. So here let exclamation mark n equals get state. So that's it. So sorry, this get state is without arguments, because here we say get state is the function without any explicit arguments. So what do I now? I can define this code, and I can say print t. And you see, in my definition here, print accepts one argument, right? T. But if I say print t, what it returns me a function from int to unit times int. And that is because of the monadic expression, right? Because it turns this state keyword, turns any monadic expression into a pair. I pass the initial state here, 1, and it prints me the tree. It gives me 1, 2, 3, 4, my tree, and then it returns me unit value and 5. 5 is the new state. So you see, interesting thing here that I did not need to keep track of this state explicitly. I don't need to remember that I need to return a state here. I just say I return unit. But because this unit is encapsulated in state the monad, it is correctly turned into the right state. And I just say I want to get the value from state, I want to set value to the state, and that's it. And you can easily imagine situation when the state is not a value, but for example a map or a dictionary, and I can say I want to access this variable, that variable, and by implementing the state monad, I can effectively emulate imperative code. I can say I want to have variables which can change, and they will change, but the code would stay inherently immutable, and this kind of state monad would automatically convert this mutable code, like seemingly mutable code, to immutable by passing additional values as needed. Now, another very useful example of a state monad, of a monad, is so-called continuation monad. Let me remind you what continuation is. So, for example, I want, let me consider a very simple again example. I want to read the number from console, I want to multiply it by 2, and I want to print the result. In my normal functional style, what I would do, I would introduce the function read, and it would return an integer. Then this integer I would pass to double, it would return an integer, and then I would pass this integer to print. So I would say I want to read, compose with double, compose with print, and this function I want to execute. I can write something like this to put all three functions together. I can do the same in the continuation passing style. Continuation passing style is an explicit way of writing code in functional programming, which would execute in kind of predefined order. So I can say, okay, I want to define the function read, and I pass a continuation to it. The function read reads the value, and then it calls the continuation function, providing x as an argument. And then the function double would take an argument x and continuation of x, and I would pass the x times 2 to my continuation function. Then print would do the same. It would take the continuation function and pass kind of useless unit value to this continuation. So you see continuation passing style. In continuation passing style, every function accepts as a last argument the function which it should execute next. So in this case, I would say read, and then I pass a function which takes an x, and then it calls double, passing this x, and then it calls function print, and so on. So I can introduce, of course, this simplified notation. Instead of composition, I can use this kind of calling dollar sign, and I can say I want to read, and then double, and then print, and then I invoke the identity function at the end just to finish this continuation with some kind of useless functional call. So why continuation passing style is important? Well, in functional programming, continuation passing style is the way to emulate imperative code, where I always know what happens next. And also, I can use continuation passing style to get rid of recursion. We have, I think, already discussed that earlier in the course when I used continuation passing style to get rid of non-tail recursion in tree situations. When I have binary recursion, I can still make it tail recursive using continuation passing style. So how can I use this continuation passing style? How can I define it using monads? It looks like a very good fit for a monadic implementation because like monads are exactly about that, about assembling pieces together into conveyors. So in this case, what a continuation monad is, I say I want to build the continuation of type T, and this continuation of type T would be like a function which takes this type T as an argument, calls a continuation function, returns S, and then it gives back the value of S. So the bind in this case would work like this. Bind would return a continuation. So this continuation function C. So I'm binding the monadic value, continuation monadic value M with the function F. So what I return the function C, which invokes this M, which calls the function M, which I am binding, and pass as a continuation function of A, which calls f of A of C. So it calls this function f, which is a function with continuation style, on the argument A, providing the continuation C from here. So what return does, return is like a value 5. I want to continuation passing style value 5. So it means that I take the continuation function and I apply this continuation function to my value 5. So you see that is the way return works. So my example with reading and doubling the number would be written like this. I say continuation passing style. I first read the value, let exclamation mark, because when reading I return a monadic continuation passing value. Then I double the value, I get another value x prime, and then I print this x prime. And I pass it to the identity function. But it looks a little bit useless at the moment, but look how can I use that to implement something like quicksort. So if you remember probably, quicksort is a sorting algorithm which splits the list into two parts, and then it sorts both parts and assembles them together. And it splits the list into two parts by partitioning it into elements which are smaller than certain value and bigger than the certain value. So why this quicksort is not like, what is the drawback of quicksort? It's of course one of the quickest sorting algorithms, but it is non-linearly recursive. It is like binary recursion, which means that, well, it means that we need some kind of a lot of recursive calls. And if we want to make it into a tail recursion, if we want to convert it to tail recursion, we cannot easily do that because it cannot be easily done with a binary recursion, but it can be done with continuation passing style. And if we want to program quicksort with continuation passing style, it becomes a little bit a pain because I need to pass an extra argument. I need to this extra argument to go around my call tree. But with continuation monad, it becomes much easier. So what I do here, I put continuation monad around the whole algorithm. And then I say, okay, like the algorithm itself is very simple. For empty list, I return empty list. I return because it's a monadic return. It means that instead of empty list, I return a function which takes a continuation, and then it passes empty list there as the result. And then what I do, I partition my list into two parts. I say list.partition, and so my list, original list, is split into head and tail here, x and xs. X is the first element. I partition it into two parts with elements which are less than x and more than x. So those are L and R. Then I sort L and sort R. And when I call sort, I use exclamation mark. Exclamation mark, it means that I invoke those functions which return monadic result. And then I assemble back. I say left part, and then I append x, and then I append the right side. And when I call this embedding sorting function, I pass the list, and I pass the identity function to terminate the continuation passing style exercise. So you see, this is like very easy way to write continuation style, because I write almost an algorithm of quick sort. I don't need to deal with continuation. I almost write in the normal way, but behind the scenes, much more complex machinery is assembled, and this is turned into tail recursive function. So that is that completes my lecture on category theory and monads. If that was a little bit difficult at the first place to listen to, then probably you can just like do it again in a few days. And I definitely recommend you again to read the blog post series by Bartosz Milewski called Category Theory for Programmers. It's a long series of blog posts, but if you go through it, you would very much expand your understanding of theoretical concepts of category theory. And because it also contains some examples in C++, it would be easier for you to see how this can be applicable to your real life imperative programming languages. Just to iterate how useful it is, when I worked at Microsoft, Bartosz Milewski was invited as the guest talk speaker with a long, I think it was like several hours long workshop for advanced developers at Microsoft, talking about exactly those topics, category theory for programmers. And like for more simpler introduction to monads, you can have a look in the Haskell handbook. There is a book called Learn Haskell for Good, and also like using the link here, the chapter 15 for monads contains like simplified introduction to specifically to monads and not to the whole category theory. So maybe you find it easier to first read about monads in the way not related to category theory, and then again listen to this lecture. So as the conclusion here, the category theory is very abstract mathematical theory which studies basic algebraic relationships between objects. And interestingly enough, it is applicable to many other areas like physics and topology. Why? Because it operates on very natural algebraic structures, and the world around us is somehow based on those principles, on those simple associative principles. Like if you can go from A to B, you can go from B to C, it means that you can go from A to C as well. And that kind of basic logic is embedded into category theory. And thinking in terms of category theory allows you to introduce some useful concepts in programming. And I definitely recommend you to get deeper into this, even like after maybe finishing our course. Thanks a lot. Thanks for watching, and have the great day and great time learning more category theory afterwards.